Hey there, and welcome to the third episode on deep learning and neural networks. In this episode, we'll be discussing a groundbreaking algorithm that serves as the cornerstone of deep learning. The perceptron is a type of artificial neural network that serves this role, and is one of the earliest algorithms that has played a significant role in the evolution of artificial intelligence. Its birth is in 1958, when an American psychologist named Frank Rosenblatt introduced a machine that could do image recognition. Frank builds it for the purpose of recognizing some images, and he thought it will eventually be able to learn more complex patterns so that it can be applied beyond image, like speech and language. For testing the machine, he gave it some pictures of different people and said to classify them. The images are just photos of people, which he needs to classify as men and women. Surprisingly, the perceptron did it with a high degree of accuracy. This news circulated all over the artificial intelligence community, and it was the time when scientists and researchers began to see the potential of neural nets to solve complex problems. It was Frank's perceptron model that opened the door to a whole new field of research. It paved the way for many modern technologies that use artificial neural networks, including image recognition, speech synthesis, language translation, and many, many more. So, what's the idea? How does a perceptron work really? Let's see how. Perceptron is indeed a simple artificial neural network that holds some input lines and output lines. You can think of it like a single neuron in the brain. A single neuron inside your brain has a large number of signal receiving and transmitting structures, what we call dendrites and nerve endings respectively. In the perceptron case, the signal receiving structures are called input nodes, and signal transmitting structures, the output nodes. For each of these input nodes, we assign some weights. And these weights are basically the key here. These are just numerical values that determine how important each piece of information coming in. In other words, the weights decide the strength of the connection between inputs, and how each input is influencing the results. So, in a way, the weights can be considered the heart of the perceptron. When an input is given, it just finds the weighted sum of inputs, and then it is passed through some function to produce an output. A little confused, right? But let's clarify it. The first process here is to find the dot product of the inputs and weights. You might have learned about dot products in your high school linear algebra classes. A dot product is just the scalar multiplication of numbers inside vectors. When doing dot products of the weights and inputs, we'll get something like this. Let's call the result with the name z. The z is then passed through something we call an activation function. So, what is an activation function? Activation functions are nothing but non-linear functions, which decide whether the perceptron needs to be fired or not. In fact, a linear function is linear, or in another way, it's continuous, meaning that, if we gave an input value of x, we can approximate the output value y, just as in linear regression. But, a non-linear function is discrete, meaning that it can determine if the predicted value for an input x is greater or lesser than a given threshold or not. For instance, let's take the case of a non-linear function shown here. If the dot product of weights and inputs gives a negative value, the activation function will not fire, but, if it is a positive value, it simply fires. This particular non-linear function is known as a ReLU, or rectified linear unit, and is commonly used as an activation function in neural networks. Activation functions are of many types. The common activations like ReLU, sigmoid, heaviside, sine function, are commonly used. But, two of the activation functions are often used in perceptrons. It is the heaviside and sine functions. A heaviside function will return 0, when the weighted sum of inputs is less than 0, and return 1 if it is greater than or equal to 0. Meanwhile, a sine function will return 0 if the weighted sum result is 0, and return positive 1 and negative 1 when the weighted sum of inputs is greater or lesser than 0 respectively. Coming back to the example Frank used. An activation function will take the dot products of inputs and weights, and if the result is a bigger value, it is classified as male, and if it is smaller, then it is classified as female. Alright, let's give another example with numbers. Let's suppose we gave 3 inputs, 0.2, 0.5, and 0. And the weights are assigned correspondingly. The algorithm will find the weighted sum of inputs. In this case we got 0.22 as a result. This result is then passed through, let's say, a heaviside function. Since the value is greater than 0, the Heaviside function fires it, and returns 1 as the output. But, here is a small problem. As you can see, when the input is 0, it does not do anything to the final result, even though the weights given are high. This can be problematic in certain situations, where the input data may be 0 or close to it. However, there are ways to overcome this limitation, such as implementing a bias term in the algorithm. A bias can be added to the weighted sum of inputs, and then the whole term is supplied to an activation function. This bias will help to shift the activation function to either left or right, as required during learning. Including bias in the term will give the algorithm the flexibility to adapt to the training data. For example, here is a linearly separable dataset. Let's say we got a line that separates this data just like this. In fact, this line is not the best, since it's not truly able to separate the blue and red data points. So including a bias term will help us to move this line back and forth. This is what we call flexibility. So including a bias term will give us more flexibility than without one. And that is what happens here as well. Shifting the activation function is really needed sometimes, to attain this flexibility as we talked about. Because of that, the important features in the training samples will not be missed. So, in our algorithm, a new bias node is introduced along with the input nodes. Then, the final output including the bias term can be written in the expanded form. Instead of writing in expanded form, which can be time-consuming and tedious, we can make a generalized form to represent the weighted sum of inputs. It looks kind of like this. This term phi is the symbol that represents the activation function. And this term is the weighted sum of input, holds inputs and weights, plus a bias. Okay, that's about the working. But what about the learning? Now we come across the most intriguing part to discuss. Even doing all of this, there is one thing that is super important for all kinds of machine learning algorithms. The learning. How does a perceptron be learned? By learning, we really meant to find the best weights and bias that makes the algorithm smart. Smart in the sense, the ability of the algorithm to learn something from the given data. A smart perceptron can eventually understand the patterns in the given data through adjusting the weights and bias. This process is known as learning or training. For the purpose of training, Frank himself proposed a training rule, which is largely inspired by an important rule in neuroscience. Known as Hebb's rule, or Hebbian learning. Hebb's rule says, when a biological neuron triggers another neuron, the connection between the two neurons grows stronger. This can be observed in our real life too. Let's say you are learning to play any musical instrument, like the piano for example. When you play it, there are some specific neurons inside your brain that activate every time you improve. This makes a strong connection between the neurons responsible for learning piano. And after a lot of training, you'll become a master of it. This is the main idea used in perceptron learning. For training a perceptron, the variant of this rule is used, that take into account the error made by the algorithm. Errors are misclassified values. For instance, it's like classifying an image of a person as male, which is female actually. The first step in training is to assign some random weights and bias. Then by finding the dot products of the inputs and weights, and adding a bias, the prediction is made. It's obvious that there must be a lot of misclassifications, since the algorithm just started to learn. These predictions are subtracted from the actual values, so that we'll get the total error made by the network. So, we got the error. What next? The next thing to do is to find a way so that the errors can be reduced. Well, what are the ways this can be achieved? Okay, it's not possible to change the inputs, so there is only the possibility of changing the weights and bias. So, by updating the weights and bias each time, the errors can be reduced, right? So by using the training data, and the error made in prediction, we can update the weights and bias. So this process of making the predictions, finding the error, updating the weights and bias to reduce the error will be repeated for a certain amount of time, until getting a satisfactory result. And this is how a perceptron learns. The update rule for weights is shown here. This term is the newly updated weights, and this is the previous value of weights. This Greek letter, eta, term points to the learning rate. Learning rate is the number of steps the algorithm needs to take to converge into a solution. We'll discuss more on learning rates and stuff in the upcoming episode on multi-layer perceptrons, so please do subscribe. By the way, this term represents the error made by the network, multiplied by the input values. Same way the bias can be updated like this. Using these two update rules, the weights and bias are updated in each iteration, causing the error to be reduced and the accuracy to be increased. Alright, to further clarify how things works, it's good to see the code implementation. So, we are just getting into it, the implementation of Perceptron using Python. And we are doing it from scratch, only with NumPy and scikit-learn, so, let's see how. This is the code for creating a Perceptron class from scratch only using NumPy. Here, this piece of code is used to create instance variables, including the initial weights, bias, learning rate, and iterations. This is the code implementation of the heaviside activation function, which accepts some input z, and converts it to a non-linear value. The fit method is where the training begins. It accepts two inputs, x and y corresponding to the training data and labels. This code is for initializing random weights and bias. The outer loop will go over a range specified as iterations at the top, and then the inner loop traverses through all the values inside the training data. Here, we are finding the weighted sum of inputs, plus the bias. And then it is passed through the heaviside activation function. Finally, we are updating the weights and bias as specified in the update rule. One more thing you can see is the predict method, which does make the prediction using the newly optimal weights and bias. For the complete source code, you can check our article about Perceptron. Okay, now let's end this video by discussing some limitations of the Perceptron. Even though it is a revolutionary algorithm as many scientists thought, it has some great limitations as well. First, it is a simple linear classifier as we know, and because of that, it cannot able to solve the XOR problem. So, an XOR problem is some kind of problem, which is impossible for a linear classifier to solve with high accuracy. Even if we fit a line here, it cannot fully separate the two data points with an accuracy greater than 50%. Because of the inability of the perceptron to solve the XOR problem, it will not perform well in some complex data, including speech, language, high-end image processing, etc. However, in the 1980s, a computer scientist named Geoffrey Hinton finds a great solution to these problems. He noticed that some of the limitations of single-layer perceptrons can be eliminated. It is possible by stacking them all together to form a multi-layer neural network. This results in the emergence of a new algorithm, the multi-layer perceptron. This multi-layer perceptron or MLP is also known as plain vanilla neural network. Apart from single-layer perceptrons, MLPs have multiple input nodes, hidden nodes and layers, and output nodes. More about MLPs will be discussed in the upcoming episodes. Anyway, the invention of MLP solves most of the problems with single-layered perceptrons. And it is also able to solve the XOR problem. This concept proposed by Hinton powers all the modern architecture of neural networks, including CNN, RNN, GANs, and more. Don't worry, we'll discuss all of these in the upcoming episodes, so do subscribe and please leave a like. So, in the next episode, we'll be discussing the concept of multi-layer perceptrons in depth, from its basics to code implementation from scratch. Thanks for watching, and we'll see you in the next one. Until then, cheers.